of length L, radius R. So what's the area of this curved surface? Of the curved surface, what's the area?
L pi r squared 2 pi r minus L.
So I like to think of it as the circumference multiplied. If I can fill that surface with rings. So it's the going around 2 pi r and then times L. So that's 2 pi r L. What's the area of this face? Now that's a circle, right? So that's pi r squared without the 4, right? But what's the volume of this thing? What's the volume inside? Then how can I fill that volume? I can think of this as a disk, right? And the area of this disk is this, pi r squared, right? And then I multiply by the number of disks that I can, let's say if I want to think of it that way, you know, just, I can fill that up with disks, and that'll fill the volume. And again, if you, like for the curved surface over here, if you have trouble remembering that, well, remember the volume inside and differentiate this with respect to R. What do you get? Which is this. So if anything, right, remember this, and remember this. And then take a derivative with respect to R, and that'll give you the area somewhere. You know, just as a shortcut. But so here an important question over here, right? Your question here was the problem here or was the problem here?
It was the area.
Yeah, so because you have E dot with the area. And my Gaussian surface is this one in red. And that one has radius R, not A, not B. So 4 pi r squared, it's a sphere. That's this. Now,
But you said the charge doesn't exist outside of the.
that's right. The charge is in here. I'm imagining a surface that doesn't exist. The surface doesn't even exist. And the surface, I imagine it to be passing at the point where I'm asked to calculate the electric field. If you want me to find the electric field over here, then my Gaussian surface has to pass through that point. That doesn't mean that the charge has to, there's no charge over there. I mean, I'm trying to find out the electric field here produced by charge somewhere else, right? But it doesn't have to be there, the charge itself. So, right? But I need to enclose all of it. Right? Because then on the right-hand side of Gauss's law, this is all the charge inside the surface that I imagine. And I don't care where it is. We did a problem last time where some of it was here and then there was a point charge at the center, you know, so it doesn't, all of this doesn't have to be at the center, that one doesn't have to be, it doesn't matter where it is. Yes? So my Gaussian surface is, because this is the electric field at the surface, at the Gaussian surface. So if I want the electric field over here and I imagine a Gaussian surface over here, this Gaussian surface is not passing through this point. Right? So this has to be the electric field at the Gaussian surface. Therefore, that's why I have to imagine the Gaussian surface passing through that point. So that then this is the electric field at the surface, and this is the area vector of that Gaussian surface. And I gotta consider then the dot product between them. Yes? And that's why doing a lot of these examples is it gives you like a new perspective, right? Okay, we're supposed to end at 5:30, is it? Or?
Yeah, 5:30.
5:30. So, let's see. Let me do. Let me end on this note, at least for today. Suppose we have a line charge. Plus. This is the 2-second answer. Correct? Suppose this is, the charge of this is, well, something that I'm going to write down. All right? and coaxial with it. Coaxial, co means like sharing, having the same axis. I think I saw in the homework they call this like concentric. Concentric is having the same center. You can talk about the center of a circle or a sphere, not for a wire. Right? But okay, but no, it's coaxial. That's how it should be. So suppose I have this metal, a hollow metal. Of radius A, inner radius A is hollow. We have vacuum over here. And then outer radius B. So it's a metal in electrostatic equilibrium. So here's the metal. That's the metal right there. But it's a metal. If it is charged, it's going to go to the surface or surfaces. Right? So, whatever this charge is, I'm going to use blue for this, or maybe red. Whatever that charge is, I'm going to call this 2, and this one 1. Whatever that charge is, where is it going to go? If it's a metal in electrostatic equilibrium? To the surface. But this metal has two surfaces. It's got an inner and an outer surface, right? Yes?
Yes.
Okay. Suppose that this wire has a charge period length of, I'm going to say it in a little bit. And the metal has this charge, lambda 2 per unit length. Well, this charge, lambda 2 on the metal, some of it is going to go to the inner surface. Let me call it lambda prime to be consistent with the notation that we used last time. And the rest is going to go to the outer surface, right? Lambda double prime. So suppose that the charge per unit length on the metal is 5 coulombs per meter, right? So this is coulombs per meter, and this is coulombs per meter. So I'm going to tell you the charge per unit length on the inner wire in coulombs per meter. Know that the charge per unit length on the outer wire is 5 coulombs per meter. So from the moment I tell you what the charge is per unit length on this wire, boom, boom, you tell me those two. Yes? Remember, this is a metal. What will be the electric field in here, inside the metal? 0, right? So that tells you something. So the charge will distribute on the inner and outer surface to make that electric field equal to 0 inside the metal, if it is in electrostatic equilibrium. Are you ready?
Yes.
Cool. So suppose I make this -1.
1,
1 and who? Correct. Okay, again. What if this is 5?
-5, 10.
Right? Cool. Right? Because remember, this has to be lambda prime plus lambda double prime. So this plus this has to give me 5. But then to make the electric field in here equal to 0, this charge has to be the opposite of that. So since this is 5, this has to be -5. That makes the electric field there equal to 0. But if this is -5 and the total is 5, this has to be 10. Because plus 10 plus -5 is going to give me 5. Yes? What if this is, I'm keeping that at 5. Huh? What if this is 0?
0 and 5.
0 and 5. Good. Is this fun? -5.
5.
Exactly. So depending on what the charge is in the inner surface, on the inner wire, it'll induce these charges like that. So that, I think I'll stop here.
So, but this can be done with all other different ones being known, so if like lambda prime was the one that was known, and lambda 1 wasn't known, like you could do it
Right.
another way.
So how about you don't? That's right. Let's say So I gotta tell you this. Oh, so let's do that. So what would you like to tell me? You're right. Yes. So suppose you say lambda prime is known. Well, what would you like it to be?
3.
3. That makes lambda 1 equal to -3. And then this one is gonna depend on what the total charge of that metal is. So if I make this 7, then this plus this has to be 7. This has to be 4. But you're right. This has to be the negative of that. Yes. Exactly. Good point. Thank you. So today is Wednesday, right?
Yep.
All day long, right? Oh, so no class next Monday, right? And so we should have a quiz next Wednesday when we come back. So, to sort of keep you honest on chapter 31. So quiz next Wednesday on chapter 21. So I'll give it at the beginning of class. I'll give you the quiz, in a piece of paper, and then you solve it, and then you take a picture, scan it, right, and then you upload it under assignments, and you don't give me that paper back. You keep it. You can keep it. But I'll grade it on the assignment, and then you use yes. All right, so you'll take it, and so come prepared so that you can, take a picture and scan it and that sort of thing. Yes.
Can I answer? I was gonna say for those of us who like take notes on tablets, you probably want us to not do this with our tablet. You want to
No, because then you could,
yeah.
exactly.
Bring it back.
Exactly. If you can, at least for the quizzes, and it would be nice. And the exams, the same thing. Just minimize exchange of stuff between them. Yeah. All right, people, have a great weekend. It's gonna be a
Wait,
long.
Professor, can you announce? I was thinking of doing it. It'd be easier to put the lecture videos on YouTube, and make it even easier would be to live stream it so it uploads while I'm streaming. But I need 50 people to be subscribed to the YouTube channel. So I would appreciate if everybody in the class did that, and I put the link in the Discord. So that's all I wanted to say.
Oh, the other thing is that next Monday, half of you do not have lab, right?
Right.
So therefore, we're not gonna have the rest of you next Wednesday. You're not gonna have a lab either. That way, we'll be doing the same.